you can hear me. There we go. That's more like it. So my sincere apologies for just zoning out on Prince there. Now you can hear me. Hi, everyone. Welcome to All Space Considered. Hello. And so if you have never been to All Space Considered, this is a monthly program on the first Friday of every month, and we talk about space stuff. So I hope there's a bit of a
little bit
feedback. So I say we all pull our chairs up about a foot. 1, 2, 3, go. How's that? Did that work better? Yeah, because the speakers are right behind us.
It's worse, actually.
It's worse.
Hello.
Check, check, check. We did our check earlier. All right, we'll let the guys in the booth play with it for a little bit, and then maybe they can figure it out.
Right up against them, the speakers?
Yeah, well.
Oh, yeah, we'll go way back there. But then we'll be sitting on the air conditioning, and it's really cold. Because you see these vents, that there's whoosh. And so sometimes by the end of the show, if we're like this, it's because we're sitting. Anyway, for the people who've never been to All Space Considered joining, what kind of a beginning of show is this? So let me start properly. Welcome, everyone, to All Space Considered at Griffith Observatory. How many of you have never been to All Space Considered before? Okay, I see some liars in the audience. And how many of you have been to All Space Considered before? Okay, so for those of you who are here for the first time, what brought you here? How many of you came because a friend said, hey, come on along with me to this thing? And how many of you came because you saw it on a website, any website? Wow, a number of website-y people. And here's the question we always love to ask. How many of you saw it in a newspaper? Still getting a 0 on that one. And how many of you just saw the line and said, hey, what's going on? I think I'll get in. Really? Seriously?
My people.
Yes, hello, welcome. So now you'll find out what you've gotten yourself in for. So let me begin by introducing myself. I'm Dr. Laura Danley. I'm the curator of Griffith Observatory and your host for the evening, along with, as always, Dr. David Reitzel, the astronomical lecturer, Patrick So, the astronomical theater programs manager, and Tony Cook, our astronomical observer. So we are here to tell you all about what happened last month, what's about to happen next month in space and astronomy. And as usual, as you can already tell, it's a pretty casual situation, so feel free to ask questions if you want. I will just begin by saying this is, of course, November. And November is a month where we always remember to be thankful. So I wanted to take a moment to express my deep gratitude to our staff, most of whom are sitting in the front row here. I'm going to do this wrong, but anyway, because I'm scared now. Bill, Jeff, Daniel, Sarah, two Sarahs, Jared, Katie's up in the back. Hi, Katie in the back. Our tech head in the back, Matthew, tech head. I didn't mean to, I meant head of tech, not tech head. And Juan, and especially Sean, who just celebrated his 1-year anniversary of being with us. So,
Jared.
And I said Jared.
Oh, okay.
Oh, Brendan, where's Brendan? Okay.
Brendan.
Brendan, who's been here for like a month. So we've got, been, right. So it's always you guys.
Fred's here too.
Fred, where's Fred?
He's in the booth.
Oh, okay. Anyway, thank you to all of you who make this possible. Okay, that's done for now. A couple more quick questions. How many of you are members of Friends of the Observatory? Okay, show-offs. You should show off, because that means you're making this possible. Friends of the Observatory is our sister support 501c3 and membership organization. They provide funding for so many of the things we do, most notably our school program, all those cute 5th graders that get a chance to come to Griffith Observatory on a field trip. That's all made possible by Friends of the Observatory. So if you like the future and you would like to support some 5th graders coming to this, you might consider joining Friends of the Observatory. And then the other people I love to thank are the tax-paying citizens of the city of Los Angeles, who I think just paid your property taxes. So thank you for that, because Griffith Observatory is owned and operated by the city of Los Angeles Department of Recreation and Parks. So it's made possible by the tax base of the city. And not a lot of cities have that. And so we understand how special, how unique Los Angeles is to have this magnificent observatory, and we thank you for your ongoing support. So two last announcements. One is that if you need to leave, you should go out the back rather than the side. Pretty much, I would say at least half the time, people try to sneak out that way, but you end up in a closet and it's very embarrassing. So you'll want to go out the back. That is an emergency exit. We'll take you out that way should there be an emergency, but the back is the way out. And the other thing is you may keep your phones on, but there is no cell service in here, owing in large part to this wonderful grating that's all around us and to our location on the top of this hill. And so your battery will just run out for roaming, looking for a signal. So we do recommend that you turn them off because you won't interrupt us because nothing will get through. Unless you have an alarm set to like, hey, tape the latest, not baseball game. Tape, that's giving you a sense of my age. Okay, so let's move on with the show, shall we? We have a game that we play every month called Songs and Schwag. I guess it has a name by now. Bill, tell us what that's all about.
I will. I'm going to unmute this for
Matthew, yes. So you heard pieces of music playing as you came into the theater tonight. Each one of those pieces of music, song, or whatever it is associated with one of the stories that you will see tonight. And during the course of the show, if you think of that connection, just shout out an identifying thing, the song title, or something that identifies the piece of music. And if you do that, and you're the first one to do that, then at intermission, or if you do it in the second half at the end of the show, you can come down and get a prize. Now, normally I always try to, pawn off some, well, no, they're great. They're wonderful things. But like little stickers, everybody's got our W1st sticker at this point. But we do have all kinds of cool things, including Dr. Reitzel has graciously decided to part with something from his office, which is a scale model of an Ariane 5 rocket, correct, Jared? And it's got like European Space Agency emblems on it and all sorts of interesting, cool things. But we also have stickers of the whole solar system. These stickers actually include Pluto, because it is part of the solar system. Yes. Bookmarks and stickers from various other missions. We also have one other thing that that always gets a laugh, and I always mean it seriously. We have beautiful Griffith Observatory calendars that just have one little flaw. They're all out of date. And that's what gets the laugh. But we have calendars from 2016, 15, 16, and 17. And I have a little chart here that could tell you that since they're completely unmarked, you can use calendars again. And at Griffith Observatory, we believe in reduce, reuse, recycle. 2015 calendars will be good right around the corner in 2026. 2016, you got to be patient. You got to love that calendar because it's not good till 2044. But 2017 and 2023. So. Please feel free to get a beautifully produced calendar, and that's it. Thank you very much.
Great. So, Sarah, I'm going to guess you went back to talk about the sound a little bit? Okay, wonderful, because we really do need that to be adjusted, whether it's turning down the volume or whatever it is, but the feedback needs to. Great, wonderful, especially people watching on live stream. Oh, hello, live stream people. And YouTube stream people. We're sorry for the feedback you were probably wincing over. I hope you're still with us. And so I forgot to say hello. Why don't we say hello to the people out there? Hello. Yeah. Hello, Internet.
Did you finish your homework?
Why are you watching this? You've got homework. Oh, he's allowed to watch? Okay. Okay, so we're off to a great start. So as I said, today is Friday, November 2nd, and we have a couple of cool stories. How many of you saw that SpaceX launch? It was kind of cool. SoCal SpaceX Sky Show. And then any landing you walk away from is a good one. Have you tried turning it off and on again? I don't know if you know what that might be, but you'll see. And at the point of no return coming up, then we have a guest. Yes. Oh, a guest from Jet Propulsion Lab, Dr. Mark Panning. Panning, yes. It's my eyes. I got to tell you, I'm getting the eyes fixed in about a week. So you will never have to have a show again where I'm going, I can't read my own writing. So I'm sorry, Mark, for messing up your last name, but he is a co-investigator for the InSight mission to Mars that's landing on Mars in 24 days. Landing on Mars. We're landing on Mars. So he's going to tell us all about that and answer all your questions, and then that will take us into pretty pictures and break. And then in the second half, we're going to do what we haven't done for a while, which is talk about the high redshift universe. Not really getting the high Z really makes me high C. I'm not sure about that one, but thank you, Jared. That was creative. Anyway, you can see we got a bunch of things in the high redshift universe, a bunch of stories from the solar system, and then we're going to say goodbye to two wonderful missions. We may or may not have time for a movie review, but we'll get there. We'll see how we're doing when the time comes. We had in a meeting, we started talking about First Man, and we thought, we've never done a movie review in here. So let's save that conversation and have it with our friends that come, and we could all share our thoughts on that one. So we'll see if we have time for that, but it'll be the first thing to go when we run out of time. Okay, so if you come here before, you know that we certainly love to start with a launch, and here is that launch.
4, 3, 2.
It's a SpaceX launch, Tony, from?
Liftoff.
This is from Vandenberg Air Force Base.
So now we can say the show has officially begun. We've started with a launch. This was the SpaceX launch that a lot of people saw. How many of you saw it? Yeah, a lot of people saw it. Patrick texted me, don't forget the SpaceX launch in about half an hour, and 20 minutes later I'd forgotten completely. So I did not see it, but a lot of people did, and it was gorgeous, as you can see. There was another launch.
1.
Engine turbo pump at flight speed. Engines at maximum thrust. Lift off.
And there is liftoff of the Soyuz MS-10 to the International Space Station, carrying Nick Hague and Alexei Ovchinin to the orbital complex.
Yeah, this was supposed to be a routine updating the crew on board, and there's Alexei on your left and Nick Hague on the right. Normally what we see after the launch is symmetrical shedding of the outer boosters of the Soyuz, something called a Korolev cross. And here's what a normal launch looks like about 2 minutes
just
after
there we
liftoff.
see the 4 strap-on boosters jettison, the first stage, and the strap-on boosters completing their job, dropping away at an altitude of 28 statute miles. At this point, the Soyuz is traveling at about 3,350 miles per hour.
That was from a 2015 launch. However, you can go to the next slide. The launch on this time looked different, and there were a number of things, if you were paying attention, didn't match what we were hearing with what we were seeing. First of all, the appearance of the booster separation was obviously not right. Then, shortly later, you'll hear a beacon sounding. It's a beep, beep, beep kind of sound, almost like Morse code. You only hear that during a landing. That means that there's a landing sequence in place. And then you'll hear call-outs that there's a failure of the booster, weightless conditions. Yet the NASA commentator's totally not paying attention, apparently, or wasn't given the audio. She's reporting a nominal or normal launch going on and calling off all the velocities and stuff as if the launch is going on. We also switched to an animation from the Russian Space Agency showing the stages of a normal launch. Nothing to do with what's going on. And then finally, you'll hear that they're in a landing mode, and it's not until 4 minutes after the emergency that the animation disappears and you hear the NASA commentator, well, you'll hear her say what she finally says.
So this is 6 minutes or almost 7 minutes condensed down into a little over 1 minute.
Yeah.
So the timestamp is
Do you
the
hear
lower
the
left
Soyuz
there.
making its way into space? Everything looking good, proceeding nominally.
Let me see this.
Inaudible.
And we have the escape tower for the Soyuz now jettisoned. Everything continuing nominally. 4 strap-on boosters have been jettisoned, and they've completed their job, dropped away at an altitude of 28 statute miles. Soyuz traveling about 3,350 miles an hour.
Is it emergency booster 2 minutes 45 seconds? The emergency, the failure of the booster.
190 seconds into the flight, Soyuz traveling about 4,700 miles per hour.
Don't be in a hurry. Buрлаки, copy. We are in weightlessness, according to our sensation.
They wouldn't be if they were accelerated.
Accelerate
Ballistic
their thrust.
descent command is sent from route controller. Copy.
Hearing there that there has been an issue with the booster, and we're standing by for information as we continue to get it from the Russian flight control team, but everything seems to be fine with the crew. We had good comm with them, and they are okay. We continue to wait for more information.
Launch lead.
Well, fortunately, you can please go to the next. About 30 minutes later, the capsule landed, and at least the crew cabin of the capsule landed safely on, but far away from where it normally would land in Kazakhstan. And the rescue crew got there about 20 minutes later. Fortunately, both Alec and I'm sorry, Mr. Haig were in fine condition. Here they were greeted by their wives shortly after the landing. Even Mr. Bridenstine, the head of NASA, was at the launch, so he was not far away too.
The feelings, everything that you're able, that the training lets you kind of put to the side and focus on the mission at hand, all that starts to well up. And so being able to finally hold my wife in my arms and give her a hug was just enormous. And, you know, it made me feel like, okay, yeah, I'm finally back and safe.
And so now some new materials come out, and NASA, actually Roscosmos has said what the error was. Here's actually, after the video cutaway, this is what we would have seen, more of an explosion and stuff going on. But the most important thing is the videos that just came out yesterday. This is a rocket cam view.
View here of the Soyuz making its way into space.
We've put in the sound synced with it. So.
Everything looking good, proceeding nominally.
And you'll see them.
Inaudible.
And we have the escape tower for the Soyuz now jettisoned.
So we've got it a couple more times slowed down because everybody wants to look at that in slow motion. So here it is fast.
And it's the booster on the left that hangs up on the central part and actually ruptures part of it and caused it to fail. So that triggered an emergency sequence. Yeah. Now the astronauts were gone by that time. They had already boosted off from this. And once again, this is the booster that apparently caused the rupture. Yeah.
So did that booster drive the rocket off course, is essentially what it did?
And it also kept the center one from continuing its firing. So it shut down. It knew something was wrong. I mean, it has sensors and stuff that put it into emergency mode. This is a painting, actually, that was released just before that video, but they did a good job. This is from NASAspaceflight.com showing the failure. And next picture shows, now the escape tower was already gone. That actually goes away before the booster separates, before the side boosters separate, but there's another emergency system that launched the enclosed Soyuz away. And then all that stuff had to blast off and separate for the crew cabin to land safely.
So Tony, what was the nature of the failure? Why didn't that one booster separate properly?
They called it a sensor failure, and apparently there was a rod that was bent that apparently kept it from detecting the separation. And so it's some kind of manufacturing problem. Now, since then, there's already been another Soyuz launch. And I believe there's at least one or two more coming up in the next week or so. And
now, does the
Patrick will
Soyuz
tell you
have
more
a
about
pretty
that.
good track record, though? It's
It
usually
has
very
a
reliable.
good, not perfect. Now, the first Soyuz launch back in the 1960s was a failure. It actually killed the astronaut Komarov, who was that crew member, due to some kind of terrible parachute problem in the capsule. There have been 2 other launches. One was an accident something like this one, and the escape tower was attached, and that produces terrible G-forces. So the worst thing that happened was that cosmonaut was shaken up quite a bit. I think there were 2 on board. And it landed in some unknown place and rolled down a hill, and they actually had to wait overnight to be rescued. There was a 3rd one in the 1980s where the booster exploded on the launch pad, and the escape tower carried the crew away safely.
But
so the
roughly how many successful ones?
Oh, I don't know. I mean, this has been going on since literally, this is basically the same booster that launched Sputnik. So I mean, it really goes back to the 1950s. The more modern ones came in the late 60s, and they've been slowly modified. I don't know how many launches they've had, but it's been a lot, and it's actually a very good launch record. Their escape system works. The good news here is that they made it,
That's right.
and it did what it was supposed to do.
So they were headed to the International Space Station to change out crew, as you said. So Patrick, what's going to happen with the crew?
Okay, well, the failure, of course, throws the schedule into a little bit of a pickle. So, and we'll take a look at the scheduling, original scheduling versus new scheduling in our next slide. And here it is in this beautiful laid out Gantt chart here. The current crew is known as Expedition 57, which is EX57, and the next crew is going to be launched is Expedition 58. Now, Expedition 57's crew have been on the space station since June 6, and they arrived on board a Soyuz craft, which is currently docked there. And the Soyuz craft has an on-orbit lifetime of 210 days, which means that they must leave by the deadline, which is January 2nd. So on this gray line here, this is the original schedule for Expedition 57. They're supposed to leave, originally scheduled, they're supposed to leave the space station on December 13th, and the launch of the next mission, 58, is on December 20th. Notice there's a gap there, and that means that gap would normally be filled if the Soyuz mission was successful. So they can't leave the space station uncrewed because they had to put an autopilot, and no one's there to look after, to seek any problems, or experiments will fail that are continuing running on the space station. So what they've done is they've asked the existing crew to stay until December 20th, and they're going to push forward the launch of the next mission to the space station on December 3rd. And so there's roughly about a 2-week overlap between the 2 crews, so they can get familiarized with the space station. So this is the current crew, Expedition 57, and we'll go to the next slide. This is the Soyuz craft, which is MS-09, which they will return on December 20th.
And is that the one that had the hole in it?
That is the one that has the hole in it, yes.
So tough times for the crew.
Right. Jim Bridenstine of NASA's administrator is confident that the launch will take place on December 3rd, and he's been reassured by his counterpart, director in Roscosmos, that will happen. And the next crew, which was basically 58, Expedition 58, slated originally for December 20th, is now December 3rd. So we'll hopefully look forward to seeing that launch.
So it was a rough month for NASA in many ways, not only this very dicey, scary launch, but also Hubble suffered some trouble.
Yeah, the Hubble Space Telescope had some troubles with one of its gyroscopes. It actually uses gyroscopes, not quite like this, but the same concept, a spinning thing, to keep it stabilized. And we have a little video to show you how that works.
It's just a toy gyroscope, really. But of course, in zero gravity, if you knock it, it's going to tumble, it's going to move around. However, if I get this spinning, so once the gyroscope is spinning, you can just see how stable it becomes. And however I knock it, it's not going to change its plane. It's going to remain in the same plane. I can put it physically into a different plane and tap it again, but it will still hold that same plane.
Now, there was another experiment where they used this old thing
Here
called
we
a
have a
CD
compact
player.
disc player, and the rotating music disc inside presents a fair amount of gyroscopic stability. The next thing we decided to do was to tape 3 of them together. So we taped our flashlight to it, and when we work at dark corners of station, like with our drill driver, we can use the platform as a third hand, and we can get to work with our drill, and we can listen to music at the same time.
So indeed, you actually need one for each axis to maintain stability. So if you have a gyroscope spinning like this, you don't have any stability to motion that turns that direction. And if you had a second one, you still have one motion that's free. So each axis has to have one. So they actually put 6 of these into the Hubble Space Telescope. So there's 3 and then 3 backup. Well, one of them failed, so they switched over to the backup, and it failed. Now, luckily, the astronauts, when they serviced it, they replaced all 6. They put 6 brand new ones in, so they thought, well, it should work fine. We'll get the old one working, or we'll get the backup working. And they fired the backup up, and it started giving very weird readings. The readings it was getting on how fast it was spinning were way too high. They thought something's wrong with this thing. So they had to come up with a plan of what to do, so they called the IT department.
Hello, IT. Something's wrong with my computer. Have you tried turning it off and on again? Oh, dear. Thanks.
So,
you're welcome, mate.
yeah, so did you try turning it on and off again? We've all been told to do that with our computers, of course, and indeed, that's what they did. So they turned the gyroscope on and off again as the telescope was being moved. So they moved the telescope from place to place, and they spun the gyroscope up, they turned it off, they spun it down, and that was actually was to reset a little sensor that's inside there. There's a little mechanical part, and they were trying to recenter it, knock it back in, and it worked. So they were able to get that gyroscope giving reasonable values again, and the Hubble Space Telescope is back to pointing okay. So we have a happy Hubble. Yay.
Yay, happy Hubble. And then 5 days after they lost the gyroscope on Hubble, they lost a gyroscope on Chandra, which is the other great observatory, but in the X-ray part of the spectrum. So what Hubble is to visible and ultraviolet, Chandra is to X-rays. And it lost a gyro, and you may sound like that's crazy, but gyros are moving parts that, you know, it's not too crazy to lose a gyro. That's why they put in redundancy. But no trouble here. They turned off the one, turned on the redundant one. It worked fine, and they were back to operations. So never lose an opportunity to put googly eyes on a telescope. Chandra was happy as well. So yeah, rough month, but everything came out okay in the end, and we'll just have lots to come in the coming months. I just wanted to touch briefly on this story because it caught so much attention in the news. The IPCC, we'll come back to what that is, which is the Intergovernmental Panel on Climate Change, says that limiting global warming to 1.5 C will require drastic action. And it was quite surprising, I thought, the way this headline just caught on, finally, everywhere. No more time, wishful thinking isn't going to be, no room for wishful thinking anymore, as in, wake up, folks, this is real, what we've been saying, and it's quite dire. So all of this headline, how many of you saw something in the news in the past month about the global warming we're really kind of, it's a yellow alert, orange alert, getting to red alert. And that all came from this report, which looks so colorful and pretty. So I tried to look above and that's the report itself. This is the home page, also not very inviting, but there's the report. So just wanted to tell you a little bit about the IPCC, which is, as I mentioned, Intergovernmental Panel on Climate Change. It is an instrument of the United Nations and was started, I think, actually originally in the 70s or early 80s, and has had 5 reports so far. They do not do original research. They don't fund original research. They summarize research from the literature. There are thousands of scientists from all over the globe, I think 120 or so countries, that donate their time to help assimilate and assemble all the data together to provide advice. Every sentence in this report then is reviewed by all nations. So when you get an IPCC report out, it's vetted and it's thought to be very, very reliable interpretation of all the data and all the science. So After, as you can see, the most recent one was 2014. In the wake of that were the Paris Accords in 2016. And if you followed that, you may be aware that the goal of the Paris Accords was to limit warming to 2 degrees, and actually they said well under 2 degrees of centigrade rise in temperature, and in fact actually gave an aspirational goal of it being 1.5 degrees centigrade. So maybe we can get to only a rise of 1.5 centigrade. And so because they didn't know, the UN wanted more research into what's the difference between 2.0 and 1.5. And that led to, they commissioned the IPCC to do another report, look in great detail at the difference both on how to get to and also what are the ramifications of the 1.5 versus 2.0. So those are numbers you're going to hear a lot going forward. And we talked a great deal last month about, 2 months ago in September about climate change. We hadn't talked about it in a year, but if you were here 2 months ago, you know that we went into great detail. So I didn't expect to do it again, but because this report is out, I'll remind just a few things. We love this graphic that shows global temperature where that 0C is at 1850. And with every passing decades, the colors go up the shades of the rainbow. And you can see the average global temperature every month for every year since 1950. And as time goes on, those colors correspond to time, not to temperature or anything like that. So indeed, in 1850, it was quite a bit cooler. And as we all know, we've had, I think, 9 of the hottest 10 years have been in the last 10 years. And so it's hotter now. There's no doubt about that. The climate has warmed. Now, I just want to point out here, it looks like we've already touched that 1.5. This is based on above the temperature, average temperature in 1850. This 1.5 versus 2 that you hear about everywhere is over an average. Sometimes it's between 1850 and 1950. Sometimes it's between 1850 and 2000. So you have to be a little wary. There's some wiggle room in different reports, but that's generally what we're talking about. And yet it makes quite a difference. Here's just another representation of the average global temperature, now colored from blue to red, where blue is cold and red, well, cooler, and red is hot. So there's no doubt it's getting hotter, and many of you have seen this so-called hockey stick diagram, where those were the average temperatures for the last 150 years or so, and then boom, the temperature goes up. If you want to hear more about this, we haven't yet posted it to our website, but we're going to post our talk from 2 months ago, and we go into this in great detail. One of the things we talk about is that it corresponds, you can see the big rise in temperatures really over the last 40 years or so, and that corresponds to a big rise in the amount of carbon dioxide in the atmosphere. This is not a mystery. Carbon dioxide acts like a blanket. It keeps the heat in. There is nothing complex about it. It's basic physics. We showed a demonstration 2 months ago. It's just how it works. There's nothing fancy. This is nothing complicated models. Sometimes they may try and make it sound like, oh, the scientists, it's so complicated. It's not complicated. CO2, greenhouse gases, act as a blanket. They keep the heat in, full stop, that simple. So this is going on. The climate is heating. And in this report, this is actually a diagram made by Thank Heaven the Guardian, who interpreted, and I saw the original IPC diagram. It's harder to read, but the basic gist. So the Guardian here made a different one, and I just have it in front of me so I can see it better. The deep purple is yikes. I'll give new words for uh-oh, and yowie, and yikes. No, I shouldn't be laughing because it's actually quite serious. As you can see, well, the coral reefs are already in sort of not doing well. The gray here is where we are now. We have in a range somewhere between about 0.7 to 0.9 degrees of Celsius on average. And so we're already into the very bad zone for the coral die-off. You can see that when you get to 1.5, just about everything is in trouble, and at 2.0, everything is really in great trouble. The Arctic will melt, the flooding becomes, dramatic, single storms, more storms, all the rest, threatened ecosystems. very seriously threatened by the time we get to 2.0 and frankly also by 1.5. So, as I say, this represents global research, worldwide research, and so there's a lot of discussion about this. I want to point out that this is a discussion of what's the difference between 1.5 and 2.0. We're on track for 3 by the end of the century. So both the world of 1.5 and 2.0 degrees rise require dramatic cutbacks of our use of fossil fuels, and as you may remember if you were here 2 months ago, that just reducing the sources of greenhouse gases is probably no longer going to be enough. That we have to also increase the sinks. We have to get scrubbers. We have to grow more forests that soak it up. We have to take proactive action that will actually remove the carbon dioxide from the atmosphere. If you were here 2 months ago, sorry to keep referring to that, but we talked at length about this idea of tipping points. And once the West Arctic ice sheet goes, and things like the permafrost in Siberia melts, and many other tipping point catastrophes is really the right word, that we get stuck in a situation called hothouse Earth, out of which we can't come back for thousands of years. So this really is that serious, that dire, and of course the consequences are not only to ecosystems but also economic. This is a picture. It looks like we photoshopped this. This isn't. This is just a week and a half ago in Venice, where the flooding is, you've seen people walking ankle deep in Venice now. They're thigh deep. The storms, of course, we just had a very severe storm, devastating storm in the United States. We like this because of the one house that was to code survived. But the economic impact is great. And in fact, this year's Nobel Prize winners in economics were both of the winners did research on the economic impacts of climate change. And in particular, the fellow on the left, I presume he's Dr. Nordhaus, in the 70s was the one to point out that if you don't take climate change into account in your economic models, that you're missing an important factor. And of course, as we've seen, that's now critical. Even the Department of Defense factors in climate change in its planning because it's happening. And so this idea that it's not happening is wrong. Yeah. Anyway, I dug out a slide, if you look at the top, from 2011. Because this was the first time we ever talked about climate change in All Space Considered, because, well, it's political. So we thought we have to talk about it, but we need to talk about a framework to discuss it. So we went through these things, and now, only 7 years later, is it happening? Yes. Is it bad? Yes. Should we do anything about it? Yes. Do anybody here 7 years ago and remember this? Can we do anything about it? Yes. So there's also this idea of, okay, it's really bad, so let's just keep polluting. No, we can do things. There are things to do. And in fact, 2 months ago, one of our regular attendees came down and said, very spirited about, we need to talk about solutions. We won't talk about it in full today, but I promise a guest in 2019 to go deep into it. But this bottom question of how can we do anything about it as well, we have to understand the source. We have to understand where it's coming from. We have to do it with open and clear eyes. We can't politicize it. We have to look at the facts. So the facts are they come primarily from fossil fuels. There's just no way around it. The carbon comes primarily from gas, coal, and oil. At the bottom there you've got something called cement, making cement, but that's not, it's energy production in a variety of ways. Transportation is a huge one. Industrial, now the way is the industrial transportation in the industrial side or the transportation side, but basically you can see the distribution of factors here. Also by country. You can see that China is the largest now, the United States and Europe sort of very close to each other. But in the last year, things have gotten better. Last year, the U.S. actually reduced quite a bit, and on the flip side of the chart at the very bottom, China, of course, more than offset that with its growth. So I thought this was an interesting graph from the New York Times. In particular, you can see the question of China versus U.S. here. The U.S. certainly was the leader for most of the time, but now you can see the little gray kind of drops down. There it is, the U.S. production, where China is jumping up. And that's why this has become an issue of global politics, and you hear it discussed in the news quite a bit. Of course, a lot of beyond the individuals, there are industries that use it. This report from the CDP, which is Carbon something project. I'm sorry, I can't remember. I'll have to get that. Anyway, here's their list of, there's the top 100 companies, and you can see just looking at that's the top 15. It's all oil, coal, it's all energy production. That is where it is coming from, period. So that's what we need to do, is to solve that problem. So obviously transportation, your homes, heating, trying to keep the thermostat down, your food, sourcing it locally, all these things, you've heard them a million times. But the two most important things, the experts say, is that is collective action. If you are worried about this, get involved with others who are worried about it. There are organizations that educate, and you can support those. But the other thing, of course, and this is quite timely, is you can vote. So usually we show furry animals. I was going to say no time for furry animals. This time it's red alert. This is not a furry animal situation, but then I broke down and we put in a few. So, but even they are voting. So think how proud you'll feel when you put that sticker on your lapel. So with that, just kind of a fun story from the Arctic or the Antarctic. You don't get that a lot.
Okay.
Oh, winner! Excellent.
I was going to vote for this picture because this was tweeted by NASA, and it was captured on a routine flight called Operation Icebridge to assess the amount of ice in West Antarctica, and they came across this really rectangular iceberg, and they saw a second one which was not so rectangular. These are called tabular icebergs, and in nature, they usually have a little bit more ragged edge and looks like the one on the right, but this one was almost perfect. But they do happen, but it's kind of rare. Also, the next picture too, which is for good measure, something that looks like a pizza. Okay, well, on to a little bit more serious stuff. So this image was taken back in 2011, and it's a flight over the Pine Island Glacier. And this is located, and we'll go to a map here, in West Antarctica, and it is actually near the epicenter where a lot of ice loss occurs. This little notch here is basically where the glacier is, and it's an ice stream. And so we're looking at animation from 2014 data. Yeah. Sorry. And you can see it's a giant ice stream that goes out into the sea and then carves. The last large carving of an iceberg at the front of the glacier was 2017, last October. Now, just recently, in fact, in the beginning of October, another crack was seen at the head of this glacier, which started forming, and you can see the progress of it. From September through to the beginning of October. And if we go to the next slide, you can see the piece that's about to carve at the head of the glacier. And how big is it? Well, it's about the surface area of 5 Manhattans. So that's really huge, but it's not as large as the last iceberg that carved from the Larsen C ice shelf. And that one was so huge, it was about the size of Delaware. And so we just wanted to give you a visual illustration, but also now that we have a comparison of Manhattans and Delawares, we can see that there's 86.8 Manhattans to 1 Delaware. There's the 0.8 right there. And there's the 0.8 Manhattan drinks without the base. And there's someone enjoying a Manhattan.
So that's our new Manhattan.
Okay. Now, since we were watching this story develop, the iceberg actually carved out, and this is the most recent. And in fact, just a few days ago, it just separated from the glacier.
Yeah,
so,
we thought for most of the month that the story was going to be about the crack, but no. It's already broken off.
It broke.
So those are some big headlines from this past month. Now we have a big headline for next month. So with that, I would very much appreciate a welcome to our speaker, Dr. Mark Panning.
Thank you very much.
Here, would you like that?
Sure, I'll run this. Here, this is great. Hello, everybody.
Before you go, let me just ask you just a few bars about your background. You have a PhD?
Yeah, I have. So my PhD is in geophysics, seismology. I started all of my work originally on the Earth, but I, obviously on the Earth, but also about the Earth. Got distracted in a postdoc on looking at other bodies, and now I think about Mars and icy moons for the most part.
Did you imagine you would do this when you were young? Or were you thinking about the Earth only as a kid?
I thought I was going to be maybe a mathematician or maybe a chemist or something like that, and then the geologists were more fun.
It's true. I understand that. we have said in this show that the geologists are the biggest drinkers.
Yeah, they are.
The astronomers are second, but geologists.
Geologists can drink. There's no doubt about that. And they're also really good at bad puns. I don't know if people could hear. There was an on the rocks joke over there. Yeah, should I?
Please do.
Okay,
Tell us about InSight.
So I'm a co-investigator on InSight, which means I'm on the science team. JPL is full of engineers for the most part. They keep our scientists around as as tokens. We're mascots maybe. Regardless, InSight launched on Cinco de Mayo. And we're now just, about 4 million miles away from Mars, something like that. And we're landing on the 26th. So basically, what's different about InSight compared to most Mars missions you've probably heard about? Most Mars missions look at the surface. The whole point about InSight is we're trying to look inside of Mars. So, and the reason why we're doing it, I always have to justify myself to people. So I say the reason why we're looking in Mars is to understand how rocky planets form. And one of the 4 rocky planets that in the solar system, of course, is the one we're sitting on. So we're trying to understand how planets form in general. And so this is just a picture of those 4 rocky planets plus the moon. We got all these cartoons of what they look like on the inside, and you notice Mars is over there on your right, and there's not much detail in that cartoon. We're out to put the detail in that and to understand how Mars formed and evolved. So we have good data on the Earth and the Moon for the most part, and not so much about the other planets. So we know that the Earth, when I say warm and very active, I'm talking about inside. It has a lot of heat inside that's getting out, and that's what drives the things we see on the surface of the Earth, things like plate tectonics, earthquakes, volcanoes. It's all being driven by heat in the inside getting out. We know the Earth is warm and very active, but right next to us we have the Moon, which is much smaller and lost its heat very early, and so it's cold and mostly quiet. It doesn't have a lot of quakes. We actually did have seismic instruments on the Moon, so we know that there are moonquakes, but they're very small and very few. Mars is going to be somewhere in between, and it's going to by observing it, we're going to learn a lot more about how active it is and how it evolved over the last 4.5 billion years. So there are two main sorts of goals we have with InSight. So this slide's the first set of goals. These are the ones about looking at the inside of Mars. We're not actually going to cut it in half, of course. That'd be really cool, though, but probably we'd get in trouble with planetary protection. So anyway. Yeah, so anyway, we're going to look for the size of the core. This is actually a really open question. I'll get back to that in a little bit. What it's made out of, we know it's mostly iron and nickel like the Earth, but there's other things inside of it. And depending on how much it is, it changes the density and how big it is. We know the gravity of Mars, but that tells us a trade-off between how big the core is and how dense it is. But this is going to get to the details. We also are going to look at the crust. If we know how thick the crust is, we know more about how much Mars has melted in the past, because everything on the crust, the thin edge around a planet, is stuff that's melted in the past. And we're going to look at the other structure of the interior. And a real critical point is to look at how warm the interior is, because that's what drives the process. Mars is a little weird that it's had volcanoes. For example, Olympus Mons is the largest volcano in the solar system. It's really big, and it's been erupting in basically the same place for billions of years. That's really strange, and understanding why Mars is doing the things it does requires knowing what's happening inside of it. I'm a seismologist, so one of the cool things I want to know about is how often Mars quakes happen. I've spent a lot of time over the past 10 years that we've been working on putting together InSight arguing that there will be Mars quakes that we can record. I'm hopefully going to be proven right here very soon. But that is a primary delivery. You know, how powerful these Mars quakes are. We know it's going to be quieter than the Earth. We also are very certain it's going to be more active than the Moon, and so this is going to nail down better those details. And the interesting thing is, a lot of the quakes we saw on the Moon were actually impacts. Actually, the biggest quakes observed on the Moon were the impacts from the Saturn IVB stages. So those are the biggest things recorded on the Moon. We should be recording impacts on Mars as well. Well, there's an atmosphere on Mars, so it filters out a lot of the little guys, but we should still see impacts. Yeah, well, yeah. We're impacting very gently. So here's a picture of the lander. For those who have followed Mars landers, the picture of this lander might look a lot to you like Phoenix looked like. That's because it's really the same spacecraft as Phoenix. It's built in Lockheed Martin, everything's the same basic design. Our arm that we use to position instruments on the surface is the same basic arm that was on Phoenix. In fact, they left the scoop on it. I know in past editions of this, Matt Golombek has come. He was very instrumental in making sure that scoop stayed there because he wants to do geology on Mars. And I'm going to help him try to talk the engineers into letting us do that. But there are three main instruments associated with InSight. So there's the seismic instrument. That's the size instrument. It's the one kind of on the left of the screen there that looks like it has an upside-down pie plate on it. That's the wind and thermal screen. On the right of your screen is the HP cubed instrument. That's actually a heat flow instrument that's going to go down, and I'll show a little more on that later. And then our last major experiment on it is the RISE experiment, which is actually just radio science. So it's using antennas that are on there for communication anyway. So HP cubed. We love our acronyms. This one is Heat Flow and Physical Properties Probe, and so instead of writing out 3 Ps, we call it HP cubed. This is, it's basically a self-driving nail. It's a little spring-loaded hammer, and it's going to go down up to 5 meters, 16 feet, for those of us who deal in English units. Hopefully the engineers are all using the right units. I won't go down that road. So that's pretty deep, and the reason why we're going that deep is because it's trailing thermometers behind it, and it's going to measure how much the temperature gradient going out, which tells us how much heat's going out. And we have to go pretty deep because there's a daily variation that only goes down a few centimeters, but there's also yearly variation that goes down a meter or so, and we want to get well below that, so we're really recording the heat flow coming out of the interior.
Did you make it from Legos?
No, this is a cutaway view. That's actually showing all of the cabling inside it before it comes out. It does kind of look like Legos, though. The only version I usually see is one that's a 3D printed version, and so I'm used to seeing it as kind of ridged plastic, but it doesn't look like that. It looks pretty good.
Well, what happens if you hit rock?
So so that's a good question. So it's designed so that if it hits a rock at an angle, it'll just cruise around it. Okay. If it hits a rock dead on, we're kind of stuck. So once again, I'm going to reference Matt Gollenbeck a lot. He assures us that the site we're landing is going to be very low on rocks, and so hopefully he's as right as he is confident.
That is the best line I've ever heard.
Yeah, so we don't need to get down to 5 meters to get good data. We're pretty confident at 2 to 3 meters we're going to get good data. And there's a lot of evidence that there shouldn't be too many rocks close to the surface. But the seismometer is going to be out there anyway. That's what I'm most excited about because I'm a seismologist. but there's the chances for success we're assured are quite high. But we'll see what Mars. We only get one shot. We can't pull it out. Yeah, so once it goes in, the ground collapses behind it. So if we tried to pull it out, we'd just break the tether.
Turn the hammer around?
Yeah, you could try to Apollo 13 our way out of it, but
the subsurface life will just knock it back up.
Yeah, there's.
Is your seismograph, the experiment, is it similar to a geophone that you would use?
It's a much more sensitive instrument than a geophone.
Okay.
I got a figure coming up, a picture coming up later, but yeah, it's much more sensitive than a geophone. The radio experiment, I'm not going to talk about this one too much, but this is the picture on the left is showing those little green cones coming out. Those are the path of the radio waves. You can't see the radio waves normally, obviously, but they're coming out of these little UHF antennas on the side, and those are communicating direct to the Deep Space Network. I think that's probably a picture from Goldstone out in the Mojave Desert, where we do all of our communication. And they're going to do very careful Doppler ranging on there, and we'll locate our site on InSight to 2 centimeters accuracy. But we're even better on velocities, and that's going to tell us how the axis of rotation is changing. And there's this thing called nutations, how it wobbles back and forth. It's like when you shake a milk jug. You can tell how much liquid's in it by how it shakes. That little wobble of the rotation is going to tell us about Mars' core.
That was a brilliant explanation of a complex thing.
Yeah, a little oversimplified, but it gets you down the right road anyway. Here's the seismometer. So we're actually having 2 seismometers. Inside that pretty sphere there is the very broadband instrument. It's super sensitive to a broad frequency band. So it's sensitive enough that it can see motions that are on the scale of a hydrogen atom. So this is a really, really sensitive instrument. Strapped to the outside are the short period instrument, which is a little less sensitive, but short period's a bit of a misnomer. It's actually a pretty good seismometer. It's a lot better than a geophone, even the short period one.
So is it interferometer then?
No, so they're both. Well, so they're both basically mass-on spring sort of things with a feedback system, and that's how you get the broadband response. There's not actually an interferometer there. It's measuring the feedback. So where was I? So yeah, it's really sensitive. I guess that's. There's 2 different sets of 3 component sensors. Because it's so sensitive, it's also it's really good at measuring everything. So it measures magnetic field changes, air pressure changes, wind. So we also have the best weather station ever landed on Mars, so we can correct for that. So that's the other good thing we're doing. This is got too many words on it, but why planetary seismology? The PowerPoint is an art. And sometimes I'm not an artist. But this is an old picture of a paper saying what the inside of Mars looks like. And I always like to point out that for Mars, this is a cartoon. When we put this up for the Earth, I can tell you that the radius of the core of the Earth is 2,891 kilometers. And I can be that precise because of seismology, because we know exactly how long it takes a seismic wave to go down there and bounce back. We don't have that on Mars. We know how heavy Mars is, and we know how hard it is to spin it. And so with those two things combined, we can say it has a core, and it could be anywhere from about 1,300 to about 2,000 kilometers. I mean, those are extreme end members, but it's certainly hundreds of kilometers of uncertainty. And that has big impacts for what the core is made out of and what the planet is doing. So we want to go there. That's the example for the core. I can talk about the same things for the crust. This is trying to figure out those details. I got 2 slides on the history of planetary seismology because this is an interesting thing. And I like to call these the good, the bad, and the ugly. The good is Apollo missions. 5 of the Apollo missions put really good seismometers, and 1 of them put a bunch of geophones referencing that. And they actually just found most of that data in the last few years. It got lost, and it was rediscovered. It's kind of cool. But the data was recorded until 1977. It was turned off 2 months after I was born. So I'm a planetary seismologist that's lived in the era of no planetary seismology for the most part. Also very coincident with Star Wars. I don't know if there's significance of that too. There are 2 other missions that had data. 2 of the Soviet Venus landers had geophones on them that were recorded for a total of about 10 minutes. Venus is a terrible place to be. And the Philae lander also had geophones on it, but Philae had issues, which we could talk about. The data looks weird. These are pictures of seismograms. The one on the top is an Earth seismogram for an hour. The one on the bottom is a lunar seismogram for an hour. They don't look the same. You guys are not seismologists out there, but I think you can tell those don't look the same. Earth has these big impulsive arrivals. The moon, everything bounces around. Mars is going to be somewhere in between. We're hopeful it's closer to Earth than the moon.
Why are you hopeful that that's the case?
Well, so I can go into details. The moon is very broken up. Mars is going to be a little less broken up, and the bigger difference is one reason why the moon looks so scattered is because it's very, very dry. And it means that seismic waves propagate really well, and then they hit all these fractures and bounce around. On Mars, because there is water present, even if it's not liquid, it's going to increase the seismic attenuation, which damps out a lot of those reverberations, basically.
Because to hope for something as a scientist is an interesting concept. Usually you just want to know what it is. But is that because you want there to be...
It makes it easier to interpret the data if we're not seeing all of this bouncing around stuff. Okay. I'm saying as a seismologist who wants to interpret all the deep structure that I hope it looks a little more easy to interpret than the moon. We actually have good models of the lunar interior from that problematic data, but I'm hoping we'll have a little easier time with Mars data.
Got it.
Isn't the analogy that the moon, when it is struck by a meteor or launch stage of some sort, that the moon essentially rings?
Yeah, so actually all planets do that. So this is actually how I got my start on Earth seismology, is looking at these things called the normal modes, and this is how the moon rings like a bell. So the lowest frequency on Earth is, I think it's in 50-something minutes. So whenever an earthquake happens, the Earth vibrates, and the lowest frequency is that. And that happens on the moon. That happens on Mars. They all do. What the moon is like. This is more like energy diffusion instead of.
It's like fog.
Yeah, that's a good idea. It's bouncing off of all of these things and coming from all sorts of directions at the same time.
Is it a density issue? I mean, is there a different density Earth to Moon that?
It's fractures. It's very fractured down kilometers deep, because it's just been gardened by impacts for billions of years.
Right. Now, I know there are probably a lot of people with questions, so I want to make sure we leave time at the end. So
yeah, I get distracted.
Yeah, let's go forward, and so we have time for everyone's questions.
Bad and the ugly, I would say. Viking had seismometers. One didn't work. One did work, but it's in that little red circle down there, sitting on top of it, and one of its legs was on a rock, and so it's like sitting at a dinner table when one of the legs isn't the right length. It just rocked back and forth. So we didn't see much. The ugly, I would say, is that there are at least 10 other missions that were included seismometers that never got to where they were supposed to be. So that's been our bad luck. InSight's going to hopefully move us to the good luck side. I'll kind of, since we're running short on time, one of the interesting things about the Earth versus Mars is everything on the Earth we do in seismology is networks. You probably took a class at some point where where they talked about locating events, and they said you need 3 stations to locate an event, and it's like that picture on the left where you draw the circles and where they intersect, that's the epicenter. That's a lie. You can do it with 1 station. Spent a lot of time convincing people of this. Nowadays, we actually use very dense networks, and we look at waves that move across it, and we can actually say which direction all of those waves come from. And so that would be great if we could do that on Mars, but it's really expensive to land 1 seismometer. And so we're working on how we can use these single station techniques. And once again, this is too many words. I would like to put 1 set of equations because I am a nerd. I am a nerd, and so I have to have 1 set of equations. And this is really just 3 equations. I'm not going to explain them, honestly. But the point is we can look at things like there are waves that go around a planet called surface waves. They are stuck to the surface of the sphere of the planet. And Mars is smaller than Earth, which means that we have a better chance of seeing waves that go around the planet more than once. And I'm going to show a video of that modeled, not in reality, in the next slide. But the point is, if we look at the timing of these waves that go around more than once, we can figure out exactly where the earthquake is. Marsquake, sorry, wrong word. Yeah, so it's basically the timing of the 3 events. It's 3 equations, 3 unknowns, and my daughters are taking algebra right now, so they can figure it out. I'll try to maybe give that a problem for them when we get home.
Dad.
They hate me. And so that gives you distance. And if you can look at how the waves come in, there's a polarity. It tells you which direction it came from. So that tells you where it was. And the figure on the right is just there's a group in Zurich who have put this all into a nice GUI, and they can just do this on the fly when we get the data. I've been sending them fake data, and they've been practicing. So hopefully the real data is as good as my fake data. We'll see very soon. So my colleagues at Zurich also made this video here. So the glowing waves are actually those surface waves going around the planet. And so they go past the station. That first big bump in the wiggle on the left is that first orbit. We call it R1. Then they're going around the planet. You're not going to see R2 get there. It's going to be while InSight's still on the backside of the planet. But you'll see a wiggle come in the top left there here pretty soon. Very soon. There, that's R2. That's the one that came the long way around the planet. And then finally everything's coming back together on the other side of the planet from where the Marsquake is. And then it's going to go past, and it's going to go past InSight again. And that's that 3rd orbit. And once we've got those 3, we can do locations. We can actually do locations for closer events too. This is just, I think, an interesting way of showing how it works. So, you guys can read those, but
we can.
Except for they gave me a new background, and they put this they put this glowing sun in the background, and now you can't read anything. I love JPL, but sometimes some of these pictures, I use very boring backgrounds normally. I'm happy to answer questions, I guess.
I definitely have a couple questions, but let's take some from the audience first, just so that we're sure there's time. Yes, in the very back.
So on the rare luck that you might catch an impactor hitting Mars as versus an earthquake, would you gain any additional information?
Yeah,
for a Mars earthquake versus a impactor?
Yeah, so we've worked at the probability. We're expecting to see a couple impacts during the 2-year nominal mission. And we definitely do gain something because we already have agreements working with the high-rise camera so that if we locate something that we think is an impact, they're going to take pictures of the area. And then we'll know exactly where it happened. So one of the problems we have in seismology is we want to know about the source, and we want to know about the structure in between. Everything we're trying to figure out is looking at waves that go between the source and our location. And if we don't know exactly where the source is, then there's this trade-off between what the structure is and what the source is. And if we have a picture of the source, we know exactly where it is. And so that really eliminates a lot of the uncertainty in our understanding of what's happening inside.
I'm going to ask in the dark, shady part. It's hard to see you guys, but I want to make sure I don't miss anyone up there. If you have a hand up. Okay. Yes.
More question about the moon being fractured. That's I guess you said a few kilometers deep, but
yeah.
How deep do they go? That's really interesting. I've never considered anything the size of a planet being fractured to any continuing extent. It's all plastic.
Sometimes they call it a mega regolith on the moon, although that's become less popular these days, but it's still fun to say because it's a little rhymey. But yeah, so the very surface is just totally broken up. So the first few meters are just totally broken up, but those fractures still extend pretty deep. The moon is really cold, and so it's cold and brittle down to fairly deep. So yeah, the fractures go pretty deep on the moon.
Yes, in the back.
As long as you're probing, are you going to look for organic material as well?
There's nothing on there to measure that, so we wouldn't have any way of making that measurement. I always it's interesting to me because I always just dodge biology classes as much as I could. Life's too confusing. I can deal with physics, biology. I don't know. It's too complicated for me. So.
Yes.
Yeah, I've noticed. How long is it going to last on what is the extent of the mission? I noticed you had solar panels on there to consider a nuclear source for fuel.
Well,
last thing, will it help us understand the magnetic field loss of Mars?
Yeah, so we do have a magnetometer on the craft, and we're going to be monitoring it, and it's actually a good way of adding to our magnetic knowledge compared to the orbital observations. As far as the duration of the mission, our primary mission goes 1 full Martian year. So we are near the equator so that we can be on year-round. There was a big deciding factor in where we landed. And they've modeled how much dust will accumulate on the solar panels over time and added up all the worst case scenarios, and we should be able to last a year even adding up all the worst case scenarios and not having any dust cleaning events. We expect there will be dust cleaning events. So I'm very optimistic that we'll still be running with a pretty good power at the end of that full Martian year, at which point NASA will decide whether we keep going or not. That will be up to NASA, but you know what my opinion will be.
Yes.
How will what InSight finds out affect our plans to one day live on Mars?
That's an interesting question, and it's maybe not the most direct way. I mean, certainly understanding the heat flow could affect some plans for how we do energy, for example, in a settlement. If you know how the temperature varies with depth, then you can know. I guess you'd still call it geothermal on Mars, maybe areothermal.
Areothermal,
yeah. You could probably change the terminology there. So that would be one possible impact. I view it more as just understanding how planets formed and evolved, and that's enough to justify it for me. But in terms of direct impact on that sort of thing, I'm not exactly sure beyond better understanding how the heat flows as a function of depth, which affects one possible power supply, I guess.
I'd like to follow up on that idea of how planets formed, because you see that on their website, and then, we'll learn how it formed. So can you just kind of give us the linkage between the data that you'll be getting and the thermal instrument we'll be getting and the wobbly one, the radio one, and how that tells us what it will tell us? Will it discriminate between different models? Are there different ideas that, if the slope is this, it's the slope is that, it's that?
So one of the biggest things we'll constrain is the chemistry of the core and mantle. On Earth, we have a core that's mostly iron and nickel and 10% something else. We actually don't know what it is on Earth, so
unobtainium.
Yeah, it's something lighter. People have their different pet theories. we think likely Mars has more other stuff put in because there's some evidence from tides that it's still liquid, which implies that there's probably a lot of other stuff put in there. But by narrowing down how dense the core is, we know how much light stuff's been put into it. And we also can look at what the chemistry of the mantle is, which tells us how much iron is in the mantle. And so this is telling us how Mars differentiated, or rather did not differentiate, as well as the Earth has apparently differentiated. So that's telling us about the formation. And by looking at the heat flow and by looking at the seismic velocities in the mantle, that's going to tell us the temperature going down through the mantle, which tells us how much heat Mars is held onto, which also lets us know, which also helps us constrain how much radioactive decay is going on inside Mars. So we know roughly how much radioactive decay is going on in Earth, and we know roughly what the chemistry of meteorites are, which we think are the building blocks of the rocky planets. But until we actually get data from Mars, we don't know if our guesses on what the building blocks of Mars are really correct. So by constraining that chemistry and the temperature, it's really hopefully validating our models, or possibly telling us our models were totally wrong. So yeah, that's really the main things we're looking at there.
And are the models wildly different?
Yeah, so this is interesting. So to me, because if you look at what we call our a priori models of Mars structures, the old models covered a really broad range, and then there's everybody's narrowed into a fairly narrow range of what the models should look like now. And I'm very convinced that we're going to get there, and it's going to be different than all of those nice narrow range of models we have. So it's planetary. This is a overarching theme in planetary science, is that the less data we have, the more confident we are.
Yes.
So when we're confronted with the reality, I think we're going to have to rethink how confident we are in the range of models that we're really, match what we think is going on in Mars.
I know that there are more questions, but I'm afraid we have to draw to a close now, and at break perhaps you'll talk to some folks individually.
Sure.
I know that people will want to come up to you and ask you some questions. So with that, I would like to thank Dr. Panning for that superior talk, which we enjoyed. You can stay. You can enjoy the pretty pictures, unless you want to see them up there.
No, I'll stay.
We're about to do some pretty pictures, as we often do, and so why don't we dim the lights? And we're going to start by showing you this picture. In case you couldn't tell, David Pinsky is on our staff. Oh, let's get his name back in there. Yeah. So this is his picture of the launch of the SpaceX mission, SpaceX launch that we talked about at the very start of the show. And so we're beginning pretty pictures with, as promised, a lot of really just gorgeous pictures of the launch. So David also took this one. Yeah, I know. Where were you, David?
I was in Carmel Valley, so I wasn't around here. I was at my brother's.
Got it.
I was just in his backyard where he actually has a Milky Way. I was so jealous.
Very nice. This was given to us by SpaceX. So you can see both the going up and the coming back. Yeah.
And that's with the sun behind it, so we get backscattering, which brightens that view.
And this from our own Patrick.
Yes. So you can see the. Oh, okay.
Yeah, go ahead.
I think the first the landing stage was on the bottom right there.
Oh, yes, I understand. Right there, you'll see. Coming back, yeah. Because as you know, with these SpaceX launches, the rocket launches, and then the first stage separates and comes back to the landing pad. So we failed to say that earlier, for those of you who've never seen it.
That was Teresa's time-lapse, my oldest daughter.
Let's do that again, because, yes, Tony's daughter. Yeah, and you can see it also, the light on the right going back down.
That was from near Santa Barbara.
Wow.
And there's the booster going back and the craft going on. There are just so many. There. So yes, that's how it's supposed to look. That's not an accident or blowing up or anything like that.
That burst is really just exiting the atmosphere, right?
Interaction of the first stage and second stage.
Yeah.
And going up into the
Whoa.
sun.
Oh
Yeah.
my God.
Into the sunlight.
Oh. Wow. 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 Super stage. Wow. Oh, see that?
Yeah.
Yeah. So if you think it's great to see it downrange, then you can hear also the excitement. This is from Jared in our own
Turn off your high beams, man.
Jared, where were you?
We were about 2.5 miles from our it's public, so you can just pull over and watch.
So as you know, the first stage comes back for a landing. Always drama. Will it blow up? Will it land right? Wait. So those are the sonic booms, and in fact, it landed beautifully.
There's Elon in this one.
Yeah. So yeah, that's just a still from the video that we showed, and yeah, it's a bit too much. It's just too beautiful.
And that's actually what it looked like in binoculars, as I was watching it live, and it's what it looked like. It was unbelievable. Yeah. Therese said it reminded her of the total eclipse in terms of something kind of weird and, is this real? You know, the kind of feeling that the total eclipse made.
It looks like one of those Hubble Nebula pictures or something.
Exactly, yes. So you always want to see one when it's just after sunset.
That's right.
Because you'll get all those magnificent lighting, scattering effects.
And people in Florida see it just before sunrise. They get that kind of
Yeah.
that view.
So for a few more pretty pictures, this was Griffith Observatory the other day. Yes, go blue, but sadly, you have to put in some furry animals to ease the pain. What's so pretty about this picture, Patrick?
Well, this was taken by a CubeSat that's accompanying the Mars InSight, and that circle is Mars from 8 million miles away, seen in October 2nd. So it's getting close. This is a supernumerary rainbow. There's 5 rainbows in this, and this kind of rare sight. An orbital sunrise from the Expedition 57 astronaut.
It's a pretty picture.
This is an artist that's made a 7-meter diameter moon, and it gets displayed in various cathedrals. It's actually coming to California, up to Napa.
So in fact, we have a break video about that. That's just a cool picture of Mount Rainier through an airplane window. That's if you'd like to surf off the coast of Hawaii, that's what you might see, looking down the... David Pinsky, once again.
Ran out from watching the Dodgers. And because Sarah said, no, there's lightning and rain. I grabbed my phone and got this.
So I think everyone, I mean, there was a lot of social media discussion about the reaction to Los Angeles having a thunderstorm with lightning, but it was very dramatic. I think very unusual. Not common for us.
A lot of cloud to ground too, unusual for cloud to ground.
Then we just like this. It's a waterfall that's not falling. This is so windy. It's a water going up. And then I'm sure some of you also saw these. We loved these pictures from Antarctica of food. So, honey on bread. I don't even know what that is. Eggs. Oh, it's so rude looking. And, yep. So, yeah. And that. And then my favorite picture from the past month is this one. Because it was actually sent out by the U.S. State Department as an invitation in Australia to an event at the U.S. State Department. It was a mistake. An intern was practicing the new mail system and sent that out to broad distribution.
It was really well received.
It was. It was like, I want to come to that party. This is fog in the valleys in Appalachia. That's the city lights are the yellow, the fog is the white. And then, in honor of Halloween, right, we have this wonderful Witches Nebula. All right, with that, I'd like to bring up the lights and say goodbye to our live stream audience. And we will have a second half after about 10 minutes of break. And then we're going to take you on a wild and crazy tour of the high redshift universe upon return. So thank you for being here for first half. Let's thank our guests one more time.